Welcome to T3 Day 25 of Calculus. Today we're going to continue our work with definite integrals. So we're going to find the area between the x-axis and this curve from x equals -2 to 4. Let's graph this first. Remember, it doesn't have to be a perfect graph, but it needs to be useful. So x squared plus 4 is just a parabola facing up, and we know it crosses at 4. You can put that in there. We're going to evaluate this from x equals -2 to x equals 4. So that's approximately right, like right here, x equals -2 to x equals 4. Again, not perfectly to scale, but it gets the point across. What area are we looking at? We're looking at this area right there. So what we're doing is we're integrating from -2 to 4, and it's going to be x squared plus 4 dx. So if we do this out, we have to evaluate this, not 0, this definite integral right here. And when you do that out, you have to deal with some fractions. It's a little annoying, I know, but a bunch of things cancel and add together, and you end up with 48. So you find the antiderivative, you evaluate the limits at the limits of integration, and then you get a number. That's the answer to a definite integral, a number. The next question is find the area between the curve x squared plus 4. So it's the same thing as before in terms of the function. So we still have y equals x squared plus 4 right here, same function. And we're going from -2 to 4. We're going from -2 to 4. I'll change it back to blue. So we have x equals -2, and we have x is equal to 4. Same thing, but instead of it being bounded by before, it was the, there was no bottom bound, meaning we went all the way down to the x-axis. Here, it's saying between this curve and y equals 2. Where is y equals 2? Where is y equals 2? Let's use a red here. Y equals 2 is going to be right there. There's y equals 2. It's relatively to scale. This is 4 right there. So what area are we looking at now? We're looking at this area. So what are we going to do to find that? Well, it's the same integral, -2 to 4. The upper function is x squared plus 4, and the lower function is 2. So we subtract the lower function. Evaluating this is very similar to what we did before. You do some algebra. It's just going to be x squared plus 2 dx. You do the antiderivative, and you get 1/3 x cubed plus 2x, and you're evaluating that from -2 to 4. And if you do that out by hand, you will end up with it being 36. And that should actually make sense visually. Before, when we got this one, we got 48. That was that whole area. But we chopped off for the second one, this bottom part right here. What's the area of that? Well, this is a height of 2 and a width of 6. So before, the whole area was 48, and you took away 2 times 6. Well, that's 48 minus 12, which is 36. So it does match. Here's another one that's similar. Find the area bounded by y equals x squared minus 4. So let's graph that. X squared minus 4 crosses the y-axis at -4. It goes up like this, and it goes up like this, -2, 2, and between y equals 2 exactly. So y is equal to 2 right here. So the question is, what integral do we need to find this entire area? Well, we need to know what to integrate from and to. We know that's -2 and that's 2. So where's it going to cross? Where's it going to cross? So you need to know what those points are. The upper function in this case is 2, and what are you subtracting? The lower function. You have the upper function and the lower function. Again, the upper function, y equals 2, and the lower function, x squared minus 4, and you are subtracting them. But we need to find the limits of integration. So how do we do that? We need to know when the function equals 2. So when does x squared minus 4 equal 2? Well, that's when x squared is equal to 6. So that's when x is equal to plus or minus square root of 6. When you plug in plus or minus the square root of 6, you get out 2. So it's -√6 and +√6. So let's simplify this a little bit. We have the integral of, it's going to be -x squared minus 2 dx. We know it goes from -√6 to +√6. I'm going to give you one shortcut here. You might notice some symmetry. This area is symmetric across the y-axis. So what you can do is just find the right-hand side and double it. You can just find the right-hand side and double it. So that means that this is equal to 2 times 0 to the square root, from 0 to √6 of this thing right here. Now keep in mind this question said, what is it exactly? Exactly, meaning you need to actually do this out by hand and be really careful about it. So this is going to be 2 times, it's going to be -1/3 x cubed minus 2x, and we're going from 0 to √6. The nice thing is when you plug in 0 into this, it comes out to be 0. So we just need to plug in √6. So it's going to be 2 times 1/3 times √6 cubed minus 2 times the square root of 6. This is fine. You can stop here. You don't have to go any further. You could go a little bit further. You could take the 2 and multiply it in. But since it's asking for an exact answer, this would be definitely as far as I'd want you to go, minus 4 root 6. Stop right there. You don't have to go any further. This is totally fine. And now a big congratulations, because we've gotten to the last big topic for the year, and that's going to be volume, the volume of solids that we get by revolving something around an axis. So what does this look like? Well, you can think of a clay wheel. When you're spinning a clay wheel and you have this lump of clay, when it spins and spins and spins, you end up with shapes that have symmetry around the x-axis. So, you know, if you had this curve right here, so let's say you had like that curve, and you had the y-axis. If you spun this like you were on a clay wheel, you'd end up with like a vase like this. My sketching is not the best today. Let's erase that one right there. So we're going to get all of these shapes that have a certain symmetry, but when you cut them, let's say we cut it right here, you would get a circle. Basically what we're doing is we're adding up a lot of circles. We're adding up a lot of circles. So we're going to find the volume of the solid. So this is a three-dimensional solid of revolution that is generated by rotating the region bounded by the given curves about the indicated axis. So let's graph, let's do a picture. Pictures are going to be super important. Pictures, yes, we like them. Okay, so what do we have here? Y equals 5. So let's say we had y equals 5. I'm going to draw this freeform. So let's, no, I can't draw a freeform. I need to do some axes here. So y equals 5. It's going to be, let's say right here, y equals 5. X equals negative 2, just labeling it, x equals negative 2. And let's say x equals 4. X equals 4. So we're doing this region right here. It's this rectangle right here. We're doing this rectangle right here, and we're rotating it about the x-axis. So what does that mean? We're going to take this shape right here. There's one corner, there's a corner. We're taking this blue rectangle, and we're rotating it like this. We're rotating it around the x-axis. The x-axis is, of course, this axis right here, x-axis. So if you do this rotation, what do you end up with? You're going to end up with a cylinder. You're going to end up with a cylinder. See the cylinder you end up with like this? End up with a cylinder. So we're going to use calculus to find the area, the volume of this cylinder. So what we're going to do is we're going to look at one slice. Let's say we took this rectangle right here. See this rectangle right here? This green one? I'll zoom in a little bit. There's that rectangle. So this distance right here, the radius right here, this radius is always equal to 5 because this is set right there. We know that if we wanted to, if we took this and rotated just this green part right here, what would you end up with? You'd end up with this narrow disc right here. You'd end up with this narrow disc. See that disc you'd end up with? If we want the volume of a disc, it's a very short cylinder, it's going to be pi r squared times the height. In this case, the height is this little tiny edge right here. That's going to be dx, some infinitesimally small part of the x-axis. So the volume of this disk right here, the one that has this edge, there's the edge of the disk, is going to be, the volume of that disk is going to be pi times 5 squared times dx. So the volume of that disk is 25 pi dx, 25 pi dx. What we're doing is we're going to do another rectangle next to it, another next to it, and another next to it, and we're going to go from, starting on the left, from -2 all the way over to 4, adding them all together. That's what an integral allows us to do. It adds up a lot of small things. We're going to go from -2 to 4, because that's what these bounds were, -2 to 4. And what are we integrating? Well, the area, the volume of each of those really short cylinders is 25 pi dx. That's the entire thing we're going to do right here. So what does that equal? Well, that's 25 pi x from -2 to 4. So that's going to be 25 pi times 4 minus 25 pi times -2. So what's that going to be? 100 pi. We have two negatives right there. So it's going to be plus 50 pi, and that's equal to 150 pi. Now, another way to verify this would be to do it just as the area of a cylinder. The area of this whole cylinder is just, again, volume equals pi r squared h. But what's the height of the entire cylinder? 6. The height is 6 for the entire cylinder. So that's volume is equal to pi. R is 5 the entire time, times 6. So that's volume is equal to pi times 25 times 6. And that's going to be 150 pi. Now you might say, why don't we just do this every single time? Well, here's the thing. Are we always going to have a nice straight edge here? No. The edge could be wavy. It could change. And that's exactly what we're going to do right here. So we have the function 2 times 3 to the x. 2 times 3 to the x. What does that look like? Well, 2 times 3 to the 0. Let's just see what that is. That's equal to 2 times 1. So this thing starts at 2. And it's an exponential function, so it goes up like this. And we're doing it from x equals 1. So let's go right there. There's x equals 1. And we're going all the way to x equals 4. Right? Let's say to there. X equals 4. About the x-axis. So we're looking at this region right here. We're looking at this region right here. So the way you set this up is you think of that slice again. When you rotate this around, what does it look like? Well, it's going to look like this. You're going to have a reflection down here. And then it's going to be like a circle, a lot of circles like this. Too many lines, too many lines. Let's try that again. So if I do that out a little more carefully, if I took this point and were to rotate, it's going to rotate to this point. So you're going to get a lot of these discs right here. And the one on the end is going to be this circle right there. So you end up with something similar to that vase I sketched at the beginning. So just to sketch it again so you can see it in motion. Let's say at this point, if you rotate it, it's going to rotate around, and then it's going to rotate all the way back. And then let's say I did another one right here, it's going to rotate around and then all the way back. And let's say I did one right here, it's going to rotate around and all the way back. So that's the shape we're dealing with. To find the volume, again, it's going to be, of each disk is pi r squared h. And the h this time is the same thing. It's this little tiny, if we're doing a slice like this, that little tiny thing is dx. So we end up with the radius is the distance from the x-axis all the way up to the top, right there. That's the radius right there. That radius is this function. So what do we end up with? Pi times the radius, which is 2 times 3 to the x squared. This is the radius right here, times dx, which is the width. What can we factor out here? Well, let's simplify a little. Pi, and we could put 2, it's going to be squared, so it's 2 squared, 3 to the x squared dx. I'm doing this carefully. That's 4. So it's 4 pi 3, you multiply powers 3 to the 2x dx. And what are the limits of integration going to be? Well, the left side is 1 and the right side is 4. So it's 1 to 4. So it's 1 to 4, 1 to 4. So you end up with this thing right here. So you end up with this integral right here that we need to evaluate. So now you need to remember how to integrate something like that. Remember, this 4 pi is just along for the ride. So what's that going to be? Well, it's 1 over ln of 3 times 3 to the 2x, but then it's going to be times 1/2, because you got to get rid of the 2 after the chain rule. You can test to see if that's the integral by doing the derivative of that, and it's 1 to 4. But that's it right there. So now you have to plug in 4, and you have to plug in 1. So it's 4 pi times, so you get 3 to the 2 times 1 over ln 3 times 1/2 minus, we plug now in 1. We plug in 1. Oh, by the way, excuse me. I should have plugged in 4 right there. You might have caught that. So that should be 2 times 4 right there. And now we're subtracting what you get when you plug in 1. So it's 3 to the 2 times 1 over ln 3 times 1/2. So now you can factor out, a few things. You can factor out the 1/2. You can also factor out this 1 over ln 3. So what do you end up with? You end up with 4 pi, because that's just right there, over 2 ln 3. 4 pi over 2 ln 3. Oh, you want to do some AP calculus? So we're going to factor out, we have 1/2 in each of these. We have the ln 3's in the bottom. So what do you end up with? 4 pi over 2 ln 3 times 3 to the 8th minus 3 squared. And then if you really want to go a little further, you can factor out a 3 squared from both of those on the bottom. So what do you end up with? 4 pi over 2 times 3 squared ln 3 times 3 to the 6th minus 1. So if you clean it up, 3 squared is 9, 9 times 2 is 18. You can end up with 4 pi over 18 ln 3. This is just algebra at this point. And then 4 over 18 is 2 over 9. So 2 pi over 9 ln 3, 3 to the 6th minus 1. Once we got to here, though, we were done with calculus and we were just doing algebra. The key thing to realize is we're just integrating this over and over again. Volume is equal to pi r squared times h, and h is going to be dx. The radius could be a function that's a constant, like here. The function was just this top part, but the function for the radius in this one was 2 times 3 to the x. Just be careful with your algebra.